Hello everyone! Today we are going to learn how to emit thousands of particles and make them sticky. We are going to explore how to make these two videos. In this tutorial we don't have a process or a logic before. I've come across these results by studying and exploring the pop grains node inside the popnet. This is a complex node and that's why I decided to dedicate some of my time to understand the pop grains, and then make this tutorial. I've started by reading the node information inside the Houdini documents, and I've discovered this parameter called clamping. It's down here, this one. By default, it is turned off, and this is the parameter that makes the particles stick to each other. So let's jump into Houdini. So let's start. Let's place a geonode, as always. Call it particles. Dive in and place a sphere. Let's start with a sphere. And then let's place popnet. All the magic will happen inside the popnet. So right now, if I press play, we are emitting particles along the surface of the sphere, right? So right now, we just want to place pop grains and change its values. But before we do that, we know, and if we come here, we know that the pop grains need to know the scale of each particle. So we are going to change that with the p scale, right? And we're going to use the popvop. Inside the popvop, let me increase this window so you can see a little better. Inside this popvop, we are going to use the age parameter of each particle and change the p scale according to the age. So let's put a fit range, wire the age to the value, and then the output we are going to wire to the p scale attribute. To do that, because we don't have here on the output, we need to export to outside the other parameter. To do that, we are going to use a bind export. As I explained on the previous tutorial, we are going to use this bind export, change the name to p scale, and right now the output from the fit is going to the p scale. Let's output these parameters so we can change it outside the popvop. So right click and create input parameters. You see it creates these little boxes, and if I go up, now we have the values here and we can change it outside. Before we do that, let's change the name so we can understand. So this will be the age min, this one the age max, the destination minimum will be the p scale min, and the last one, the destination max, will be the p scale max. Okay. If I go outside the popvop, now you can see you have age min, age max, p scale min, and p scale max. We want to change the particles with the age, and I want them to start in 0, and they have the p scale of 0, and when they reach like 3 seconds or 4 seconds, I want the p scale to be 0.5. Okay, so right now let me just turn off these pop grains. Let's see what it's going on. Let's place a sphere just to copy to the point so we can see what is going on, and copy to points. Wire these in, and you will see the spheres will get bigger depending on the time. See? Because we are changing the P scale depending on the age of each particle. If we go to geometry spreadsheet, you see each particle, each point, has this age parameter. Okay? And this age parameter it's changing our pitch scale. It's right here. Okay? Let's go back to our scene view. Let's turn on the pop grains. And first thing we need to do is to turn off this assume uniform radius. If we turn off these, the pop grains will see and check each p scale of each particle. So right now, if I press play, I think it's going to explode. See? Because the particles are trying to avoid each other. Okay? As I explained before, I've been studying these parameters, and the clamping is the one that is going to stick the particles to each other. By default it's turned off, so let's turn this in with 1 to activate it. Now the particles will try to stay connected and glue. But as you see, after a while they are going to start breaking. And right now, this is the magic we are going to explore. In my animation, I want the particles to stay stick to each other with a bigger force. I put like 5,000, and you will see that it's going to take a while before they break. One thing I like to do is to turn off the physical bounce from each particle. Just turn this not all the way down, but a little down, because you were seeing that some particles are going to fly away. See, these ones. So let's dial this down a little. Oops, I closed the timeline. And right now we have less particles flying away, and the particles are staying close to each other. They are sticky, and they are going to get these nice tendrils with particles, like it was a viscous fluid. But right now, one thing I don't like is that our particles are growing in a uniform way, right? You can see a sphere, and I don't like that. I want to make a lot more tendrils. Let me increase, it's 300, okay. It's going way too uniform for me, and I want to have more tendrils on our simulation. So in order to fix that uniform growth at the start, I'm going to change the emission on the first on the start. Instead of using the surface of the sphere, I'm going to emit like a noise random. So let's come here. Let's place a scatter, and you will understand what I'm saying. So right now, if I turn on the scatter, we have all these points alongside the surface of the sphere, just like inside the popnet. So right now I'm going to place a point of op, and I'm going to place a curl noise and a ramp, just to color our particles. So wire the position into position of curl noise, the output to input of the ramp, and ramp to the color. As you see, we have some points black and the other points white, and some of them gray. Let's increase this frequency. Let me try 2 by 2 by 2. Let me just increase the scatter point so we can see what's going on. Okay. No, that's too much noise, so the frequency works the other way around. So let's, this is too low. 0.5, 0.5, 0.5. Okay. Nice. And now I can delete the points that I don't want. Use expression, delete by expression, and now let's use the color. When the color is less than 0.5, it should point. Okay. See, now we have only the white points. Maybe let's go back to 1 by 1 by 1. So right now we have our particles. Just a few, not all the way inside alongside the sphere's surface, right? So right now, let's go back here. On the source, on pop source first input, we don't want to scatter onto surface and use all points. So right now we are going to use these points to emit particles. I press play. We are going to emit only on these points. Right now we have too many points. Let's use only 250. See? And we are getting a non-uniform growing. They're starting to break a lot. One thing that I want to do is that our particles are always the same, the scatter, right? And I want them to change during the time. In order to do that, we can come to the pop-up and change the offset. For example, this one. You see, our curl noise is moving on the Y position. So I want to promote this parameter. I don't know how to do only one. Let me see if I can. Let's go the way I know. It's not the best way, but I want to promote only the offset. Turn off the type. Okay, I'm promoting the offset of the curl noise. So if I come up, now I have this offset parameter, right? And if I put $F, I'm going to use the frame number to animate our offset. See? Let me increase again the particle so you can see what's going on. But right now the the offset animation is way too fast. So let's change our expression and divide it by 200 maybe. Maybe this is too slow. Too slow for my taste. Let's go to 50. Okay. So right now if I wire this and turn on the popnet, we are going to use these new particles to emit our particles, right? These points to emit our particles. You can't really see it inside. No, you can't. But it's using all the points and different positions to emit. Again, I increase the scatter. Let's dial this down again a little. And let's dive into the popnet. On the pop grains, I want to increase the constraint iterations. And I want the stiffness to be higher. So we will have a less bouncy movements on our particles. Let's dial this maybe to 30,000. And I'm seeing that our particles are increasing way too fast. So they are making a lot of explosions. Maybe they are way too big. So let's dive in on our pop-up. Let's increase this H max to 6. We are getting a nice tendrils down here. Oh, we are still getting a lot of explosion. So let's crank this sphere a little higher. They won't explode a lot. And I want to now increase the scatter to 500. Plop, 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 plop. I'm going to decrease the edge. As you see now, it's up to you to change the parameter the way you want. I'm going back to H4. And right now, all the particles, the max size will be 0.5. But I don't want the particles to have all the same size at the end. So we are going to use an expression to change the p-scale max. I want always to start on 0, but the max value I want to change it. So let's place a fit function, and I'm going to get a random number from the ID. It's important to you to use the ID and not like point number or position, because I want the same particle to have always the same max value, and you can do that with the ID of each particle. And we know a random value will change between 0 and 1, and I want to change the p-scale maximum value between 0.5 and maybe 2. So right now the particles will have different p-scales, and they will change between 0.5 and 2. If I come up, let's place a little. Okay, now as you see, we have some particles that are a little small. Let me turn off the wire. We have the particles that are 0.5 and some others 2, some others they are like 1.5. And because we don't have any turbulence and gravity and so on, the movement of the particles are moving because of the pop grains, because they are trying to avoid each other and they are doing the clumping, they are sticking. So we are getting this nice slow effect. Again, these tendrils, really nice. Of course, some of the particles are going to fly away, but look at this. Look at this tendril. So we have our simulation. We are emitting particles, not on the sphere, all the sphere surface. We are scattering, picking some of the points, and then emitting on that points. But right now they are getting the color from the point VOP, and we want to change the color after the popnet. So let's place another point VOP, and we are going to color, let's call it color VOP. And we are going to color the particles inside this color VOP. You can do this different ways. You can use the velocity, like on X particles have a gradient. For example, let's place a fit first. A ramp. I love this ramp because you can change the gradient outside the pop-up. Write the ramp to the color and the output fit to the ramp. Let's promote these values so we can change. We don't need to change the destination because the ramp needs to get values between 0 and 1 always. But we can change the source minimum and source max because of velocity. We don't really know the higher velocity. You can check on the geometry spreadsheet. Let me see velocity. Where are you? Velocity. So we have higher values. So let's maybe like this. Always when they are going up, it's could use velocity, but in our case, we didn't use velocity. On the first video, you use h, depending on the h. Let's do it again so you can understand. The h, let's put like 5. It's changing between 0, they are starting, they are going to 5. You see when they are new, they are getting the color green. I don't like the color green. Let's make it like this. Something like this. As you see, when they are born, they have the blue color. And when they are aging, they are changing to red and then white. You can use the H, but I use another one, and I use the p-scale. Again, we don't have the p-scale here, so how do you use an external attribute to change our parameters? As you could export, you can now use the bind without, not the export, the only bind, and here use the p-scale. So right now we are going to get the p-scale value from each particle, wire these into the fit, and we know the p-scale will change between 0 and 2, right? So when the particles have the higher p-scale, we'll get white. Right now we don't have any particle on 2 scale. We have a lot of maybe 1.5, 1.9, that. When they have medium, like 1, they get red, and they are really small, they get blue. When they are 0. Let's increase this, maybe this, like this. They are like, remember this is 0, this is 2, so 0.5 is something like here. Red is like 1, and let's yellow, not yellow, sorry. Need to change the colors. Just play a little. See? Now we are painting our particles depending on the P scale, and we have our animation. Of course, if this animation is way too fast, you can always reduce the time step, so it will be like slow motion or something. So this is one way to use the sticky function. Pretty cool, huh? Look at this tendril. So this is one way. This is the second video I show you. To do the first video, I'm going to paste it. No, call it particles. I'm going to do second one, sticky cells, sticky grains. Okay. For the second one, I'm not going to delete everything. Just let's delete this one. So first things first, I'm going to emit from a circle, right? I want the circle to be on the floor, just a little bit higher, and wire this circle to the popnet. Dive in, and right now on the pop source, I want to go back to scatter onto surface. Okay. So right now we are missing a floor. So let's place collisions and place a ground plane. Let's hide this ground plane because we don't need it. And this is a mess. I don't know why it's always placing a mess down here. So let's press L. So we'll organize our node network. On the ground plane, let's dial this bounce almost to 0. The friction I want to be higher as possible. And now I want to add gravity, because I want my particles to fall on the floor, not fly away like the previous one. So right now I want to hide these. Okay. If I go up, of course I need to turn on the popnet. Silly me. But right now we are going to emit particles, and they are going to fall on the ground, but they have a huge sticky force. First thing I want to do is to dial down the clumping. For this one I don't want that higher number, maybe 200 only. Because I want them to fall on the ground, but when they reach a certain curvature, let's say like that, I want them to fall like liquid. Let's see if that works. See, look at this. Yeah. Right now I want to animate the circle position. Let's place a transform. So right now my meter is on the floor. I want, after a while, I want it to go up. So let's add keyframes on translate. To do that, press Alt and left click and you create a keyframe. Maybe on 120. Let's go up a little. And maybe a little to the side. Just to change our emission. Let's see it fall. Look at that. Look. I think the sticky is way too strong. So, as I said previous, right now you just play with the numbers, figure out what is going on. Always, if you have some doubts, you can hover your mouse to the parameter and it says a little nice hint. But if you have any doubt or any questions, go to the documents and read it. Because you can see they have a lot of information about each parameter, and it's pretty cool and pretty useful. So right now let's change it to maybe 100 because I want them to break early. That is something more. Okay. And look at that. They are building, but they are starting to break. You have these cool effects. For this animation, instead of using the P scale, because as you can see, all the bigger ones are going outside, instead of using the P scale, I used the age value. Let's crank this to 4. And I place it like a black at the end, right? Something like that. Oops, not this one. This. So if they are older, they are going to. And I use the SMIC values just to play with it. This shit is trolling me. Use it like this, something like this. See, if they are getting older, they are going to black. I think my age attribute is way smaller. Let's put to 9. Yeah, better. We have more range color. And that's it for this. As you can see, with sticky grains you can do a lot of things. I like how these fall to the ground. You have this way to work. You can emit particles and make them sticky. If I change it, let's turn this. Let's go to the, not that. Let's go to the start. Instead of emitting here, let's go here. We are going they are going to fall on the ground, and maybe they will make a nice structure. Need to reset. I don't know why they are not calculating that. That's one another approach. Now you know how to do sticky grains. You can play with the P-scale, maybe they are way too big for your taste. And this is one way, and the other way was these sticky cells that I really love. Let's cancel the, it was catching all the particles. And this is other way without gravity, so the particles will move depending on the pop grains, because they are forcing the particles to not intersect each other, but they have these clumping values, so they are making this nice animation without any keyframe. And with this effect, now play with the camera position, and you can get a nice result as this one. Hope you enjoyed this little lesson about the clamping from pop grains to make the particles stick to each other. Don't forget that you can request any art study or tutorial about any tool or node inside Houdini. Hope you enjoyed this video and see you on the next one.